I'm still worried. Isn't your theory really still a wave theory?
He's worrying about the wave particle duality that I described in lectures 1 and 2, and says effectively that I convinced him that it's particles in lecture 1, and then I did a lot of calculations of amplitudes which seemed to him to be nothing but the analysis of waves, which is the same kind of calculations that we do for waves. And why don't I admit that it's a wave theory that I'm really using? And I tried to explain that in two features about it. I chose to talk about amplitude to go from one place to another directly as a given answer. It is also possible to analyze that by saying, and I did say this, that you could think about the amplitude to go from here to here, and then the amplitude to go from there to there. And in that method of analysis, you can write it as differential equations, if you want, a mathematical form that's the same mathematically when you're dealing with a single photon as the Maxwell equations for the wave. There are two differences. First, let's take the case of a single photon. In which that the calculation of my amplitudes is precisely the same mathematically as the calculation of the electric field according to Maxwell's equations, which is a wave theory. The difference is in the interpretation of the answer. The square of the electric field, for example, in that theory is supposed to be the energy density in space. The square of the wave function, although mathematically determined by exactly the same equation, is the probability of finding a photon. So another way to answer it for the case of single photons is to say this. We calculate as if the light is a wave, but we interpret the intensity of the wave, what used to be called the energy density of the wave, not as the intensity of the light, but as the probability of finding a photon. It's that duality of interpretation which produces the difficulty, because if this were really a wave coming in, we couldn't understand how the photon counter would acquire enough energy to go off sometimes immediately when you turn it on. Nor, you see, if, for example, a wave is shining on a surface, a metal surface, we find the following, that if you shine light on a surface and you shine a lot of light, a lot of electrons come out, with each one with a certain energy. If you decrease the intensity of the light, that is, weaken the waves, you would have thought that the wave would kick the electron less, and so you get a lot of electrons out with less energy. That's not what happens. You get fewer electrons with the same energy. And when your wave has gotten so weak it could hardly shake an electron at all, you still see an electron come out with a full jab of energy only once in a great while. And that paradox has to be described by not changing. It would be a miracle if the mathematics would change, because nobody was going to play around with this wave theory that long if it didn't agree with experiment. So there's something right about those equations, the behavior of the amplitudes they were describing. It wasn't interpreted right. First. Second, I've talked about, not sufficiently, and this is a difficulty that many people, I answered somebody else this way, have with this wave particle business and this quantum mechanics, is that the first thing to do when you're giving a lecture is to take the simplest example. And the simplest example is always one particle. But suppose in the same way we take two particles, two photons. I've talked about amplitudes for two photons to come to 2 points. Now the amplitude, if you thought of it as a differential equation, is an amplitude defined. Let's take electrons, or add 2 electrons. The amplitude defined, if you understand it, I'm writing it mathematically because you asked me a mathematical question. The amplitude defined one particle at a position in space I'll call x1. It's a vector position. It's a three-dimensional. And the other particle at a position x2, that's a function of time. When there's only one particle, it's a function of x, the position of that one particle, and time. Now, it's characteristic of electric fields, of fields in general, that they're functions of position and time. But when there are 2 electrons or more, the amplitude is the amplitude to find, like the probability, to find 2 electrons, one here, one there, at the time t. This kind of a function is not a wave. It's a function of 2 positions in space and time. That's a new one. When there's only one particle, it's a function of one position in time, then it's like a wave. When there's several particles, the functions or the amplitudes we have to talk about are functions of several positions in space and time. And that's not a wave in the normal sense. And so knowing that that's the case, I emphasize with a slightly different attitude, and I know I'm talking about waves if I was talking about one particle, but not if I'm talking about more. Okay?
You haven't told us very much about quarks and gluons.
It's true that I left out an important thing because of the shortage of time. To make a complete description of these things, I'll just say it, that the quarks of each flavor, like the U-type quark, really comes in 3 varieties. We call them colors, a red one, a green one, and a blue one. They have all the properties the same. They're all the same charge and mass. They're all exactly the same. It's just red, green, and blue. That's 3 different kinds. And what are the 3 quarks that form a proton as one red one, one green one, and one blue one always. Always the 3 different ones. The way the gluons work, just to make a quick thing, I'll be done in a minute. Let's suppose that now I'm going to change the color system and draw pictures with the right colors for the quarks, you see, red, green, or blue. So if I would say I have a green D quark, okay, and it could turn into a red U quark, for instance. And in doing so, it emits a gluon, which I've been drawing as orange. But it's a special kind of a gluon. It's a gluon which if it went out, a green and an anti-red. It's like, to draw it correctly, I should draw colors for it, green and red going the other way. And what happens is if you draw these things, the colors always check out. For example, this could connect to a red, let's say it could be a connection between another quark. Let's say a red D would then turn into a green U or something like that, or a green S or something. No, I'm sorry, you don't change the type. I'm sorry. It has to, with the gluons, you keep the flavor fixed. So this is, say, a U and a D interacting. But the colors get exchanged. What the gluons do is they carry colors back and forth. And the reason why there's a 3 thing is that gluons couple to any kind of color business. So if you have a gluon, which is the green anti-red one, say, you can connect it to an anti-green blue one, for instance. If you emitted a anti-red blue one. So the quarks, the gluons, have colors. And since there are 3 colors, and you have every kind of combination, you would expect 3 times 3 or 9 different kinds of gluons. Actually, there are only 8 different kinds of color combinations. The particular combination, which has an equal amplitude to be red anti-red, blue anti-blue, and green anti-green, doesn't exist. And that describes the theory much more completely than I did before. With that game with the colors, we have a pretty good understanding of why it's only that 3 particles come together, or a quark and anti-quark. Only colorless combinations which are symmetrical in color, that don't have any bias in color, are the low energy states. And the other states presumably take infinite energy to make or something. Can't be made. So you need a red, green, and a blue. You need 3. Okay? Yes. Thank you all very much, and thank Rob for the opportunity to give these lectures. I've often thought I've never been able to figure out how to explain electrodynamics and quantum electrodynamics, and I thought that this was an opportunity to try on a poor, unhappy audience to see whether it was at all possible to explain this subject in a finite number of lectures. And I chose to come to a part of the world as far distant as possible from my home, so that if I were not quite successful, I wouldn't have to suffer so directly. Thank you very much for the opportunity and for your patience in coming all the time to the lectures. Thank you.